Welcome to continuation of our discussions on topics in abstract algebra. Today we are going to continue with the further examples of groups where we try to identify group structures from sets under given binary operations. You are welcome to illustrations. Yes, you are welcome. We'll begin with the first one. Now, let's say for the set of integers, which we denote as z. Now let mz be the set of all mx, where x is an integer. Okay. Now these sets will generate sets of multiples of z, and it is easily to identify. We can note that this set, maybe if I call it equation star, as this star, this set, okay, generates an infinite subgroup of z. Why is it infinite? Because it picks elements from z, and we know z is an infinite set, but it's a group. So z, while z is a group, mz therefore, it means what it means is that this mz is a subgroup. It's a subgroup of z, the group of integers. Okay. Like I said, it is infinite because the elements x are picked from z. All of us know that z is an infinite set. Now, we can also note that so let me call it this number 2. The left coset, which we can now write as 0 plus mz 1 plus mz 2 plus mz dash dash up to m minus 1 plus mz. This will form a set of cosets. These are cosets now. Okay. So these cosets. So if I now give it a name, for example, if I say mz or zm or whatever, let me call it like this, zm, to be this set 0 mz 1 plus mz dash dash up to m minus 1 plus mz. Now this set is also a group. Is also a group. The difference between this group and the other group is that this is a finite group. Okay. So Zm, it follows. We can now note further that it follows that Zm, okay, is a finite subgroup, and in fact it's also abelian. Okay, subgroup. Okay, of Z. Okay, why is it finite? Because it stops at m minus 1, and we know im is a non-number, so it's actually a finite subgroup. And in fact, the index and the index mz, or what we call it, zm into z. If you index it, it's going to be m. So that means it has m elements, m number of elements. So this group is actually a finite. It's a finite subgroup. In fact, we normally denote it. We can also denote Zm as Zm is equal to like this 0, 1 dash 2 up to m minus 1. Where when we say 0 dash, we mean 0 plus mz. Okay, so that means for any x in Zm, x dash is equal to 0 plus x plus mz. Now, interested readers can try to show that this is actually a group. The group operation is going to be like this. If, for example, so let me say this is an example. If H and G are in Zm, okay, then, and we can write, for example, H as H plus mz, sorry. G is G plus mz. Then we can now have some binary operation like this. H plus G will now be H plus mz plus G plus mz, and this is going to be H plus G plus mz. Okay, so this is actually a closure axiom. And we'll notice that if you want the negative, the inverse of H is minus H, and so on and so forth. So all the group axioms are actually can easily be verified on this M. So actually, Zm is actually a group. Okay. So thank you. I welcome you to next presentation. I will take another example of group.